anions. We've got a mixture of anions and cations. So let's just draw 3 for simplicity, although obviously there'll be many more. So we've got cations, which are the sodium ions, and then we've got the negative, we've got the anions. And so when the electrical current is passed through, these sodium ions, the cations, they move towards the cathode. So they're all going to go towards the cathode. So we can say that the cations go towards the cathode. And it's quite complicated to remember, but all you need to think is the cations go to the cathode. So they move from positive charge to a negative charge, because remember the cathode is negatively charged. And then the anions are going to move to the other electrode. Which is the positively charged electrode. So remember that opposite charges attract. It's just a bit confusing with the names, but it's cations go to the cathode and anions go to the anode. Just quickly answer all your questions. Yeah, the meeting is being recorded now. Yes, sorry, I forgot to start recording it. You can feel free to take a screenshot of that now. Yeah. Oh, actually, there's one more thing I wanted to mention. So when I was talking about electrodes, I said that they were metal. Now, obviously, an issue you might have seen is that we don't want the metal electrodes reacting. So they are usually made of platinum or another unreactive metal. So platinum or silver. Or any other unreactive metal. So you can work that out by looking at the reactivity series. So anything at the bottom of the reactivity series. And the reason why I've told you that is because it's usually a question that's asked quite a lot in exam questions. With regards to your question about anodes going, so anions go to the anode and cations go to the cathode. Yeah. If you've come in late, you haven't missed much. We've just been looking at the definition of electrolysis, which is this. But if you take a quick screenshot now, or it will come out later in a PDF and you can copy it up then. And then we've just been looking at this page. We've been looking at the diagram of electrolysis. So why do the electrodes need to be unreactive? They need to be unreactive because obviously, say you had, so they were made of potassium. Potassium is very reactive, and you had sodium going to the electrode. Now, the purpose of electrolysis is we want to isolate sodium ions to produce just normal sodium as a metal. And if potassium is there, then it will react with the sodium and it will produce potassium, they'll react together essentially. And so we don't want that. We just want sodium. So we don't want any reactions happening between metals. Okay, so I'll leave it for just another 30 seconds and then we'll move on to the next bit because I know there's quite a lot of writing on that slide. Okay, so moving on, we're going to have a look at two types of electrolysis. We're going to look at something called molten electrolysis, and then we're going to look at electrolysis in aqueous solutions as well. So looking at molten electrolysis, this is the easier version. So we're just, again, dealing with sodium and chloride ions. So if we just draw our diagram again, so we've got the anode, the cathode, and then, as we said, we've got the Na+, we've got the cations, and then we've got the Cl-, which is the anions. And so if we draw them out quickly again, so the anions are going to be going towards the cations are going to be going towards the cathode because opposites attract, and the chloride ions are going to be going towards the anode because they are moving from negative charge to something that's positive charged. And again, we've got this flow of electrical current. And so once the two go towards the once they go towards the two electrodes, we start to produce our products, which I was talking about before. But before we discuss that, we need to talk about why it's molten electrolysis. So the reason why we do it in a molten solution is because of the properties of ionic compounds. No, they're not called sticks, no. How do you know Na is positive? It's just because it's in group 1. So when ionic bonding occurs, sodium has one electron in its outer shell that it gives away. And if you've not learned about ionic bonding yet, it's going to be quite difficult. So I'd recommend learning about that, and then it will make sense. But when it loses an electron to have a full outer shell, when it loses the electron, it becomes positively charged. And because chlorine's in group 7, it has 7 electrons on its outer shell. So it gains 1 electron to complete that shell. And so it becomes negatively charged. So why they're ions in solution? Because they have a charge, because there's a current flowing around, so they must be charged, so they must be ions. Yeah, so metals lose 1 to become 1+, and non-metals gain 1 to become 1-. Yeah, so that should be all the questions. Yeah, hopefully. Okay, so as I was saying, so ionic compounds, when they're solid, they don't conduct electricity. And this is because they are not free to move. But when they are aqueous, they are free to move, and so they do conduct electricity. And that's obviously very important because we need ionic compounds to conduct electricity when they are in this solution, so that they can then go to the electrode and produce the products. Yeah, so as you said, yeah, only when molten, and we'll look at another situation when, actually, sorry, that was a mistake. So when they are aqueous or molten, so when ionic compounds are dissolved in water or they're molten, they are free to move, and so they can conduct electricity. So we've got the ionic compounds in the electrolyte solution. They've moved to their respective electrodes, and now we're going to start producing the products. So with the products, we write something called a half equation. for them. And so in order to write our half equation, so let's look at the anode first. So we write one for each electrode. So that's why they're called half equations, because we've got one for the anode and one for the cathode. So at the anode, we've got the chloride ions. So the chloride ions have moved to the anode. And so now we're going to produce chlorine. So we've got chloride ions, and they are going to gain an electron to produce chlorine. So they produce chlorine, which is a diatomic molecule. That just means that it has 2 atoms. So we call it Cl2. Cl on its own will never exist. And so we produce Cl2, and obviously 1 electron, because chlorine has gained an electron to complete its outer shell. However, we've now got an equation, but it's not balanced. So we need to go, well, we've got 1 chlorine, we've only got 1 chloride ion, so we're going to need 2 on the other side. So we have 2 chloride ions go to make chlorine, Cl2. The only other thing which we now need to balance is the electrons, so that we have 2 electrons. Yeah, so E- is a symbol for electrons. So in this particular situation, we are going to obtain sodium on its own, but at the anode, because chlorine has to gain electrons to complete its shell, we're going to have electrons left over with it. So that is the equation at the anode. And then now we're going to have a look at the cathode. So we've got the cations, which moved to the cathode, which were the Na plus ions. So we've got the Na plus ions, so Na plus, and these lose an electron to produce sodium. And it's just sodium on its own, not 2 sodiums, it's just 1 sodium. And that's because we have a positive ion, which is, so imagine sodium is, imagine we've got sodium like this. It's finally an ion. So it's as an ion, it's got a full outer shell, but we need to add an electron now so that we can just get sodium as an element. So we just gain that extra electron here. With regards to your question about if it's true that chlorine is present, yeah, that's true. We're going to look at that in a minute, because it's to do with aqueous solutions at the moment. We're just looking at molten electrolysis, so you don't need to worry about that for this. So with regards to your question about the cathode, will there always be 1 reactant? There will always only be 1 reactant. So there's never more than 1 reaction happening. Yeah, so it's 2 Cl minus, because Cl2 is diatomic, yeah. So with regards to your question about the oxidation and reduction, I wasn't actually planning on talking about that, but I can. So the way to remember it, which equation, so the equation for the anode and the equation for cathode, one of them is oxidization, one of them is reduction. And the way to remember it is oxidation is losing an electron, and reduction is gaining. So with that in mind, we can say that, well, the anode, it's gaining an electron, so it must be reduction reaction. The cathode, we are losing an electron, so it must be oxidation. Sorry, wrong way around, wrong way around, wrong way around. With the question for 2Cl minus 2 electrons goes to Cl2, I'm not sure. I don't think you're allowed to use minus signs in your equations. It's technically correct, but it's probably something not to look at, not to try, because it might not be correct. The question about, is the anode always oxidation and the cathode always reduction? No, it's not, but most of the time it is. So that's everything to do with molten electrolysis. If you want to quickly take a screenshot of that, then have it, yeah, you can. Okay, so now we're going to look at electrolysis in aqueous solutions. So I'm going to do this relatively quickly because we're going to look at NaCl again, but it's just a bit more complicated than the last one. So when we're looking at aqueous solutions, obviously aqueous is to do with aqueous is to do with something that's been dissolved in water. So when we're dealing with aqueous solutions, we're also going to have water. I'm sorry about the yellow background. Yeah, it's not the best. I'll try not to use it in the future. Sorry. So we have with H2O, that's split up into we have H plus ions, so the positive hydrogen ions, and we have hydroxide ions as well. So they're the negatively charged ions. So we've got our anions, sorry, wrong way around, cations, and our anions. So in addition to the NaCl, we've now got H2O to deal with. So that makes everything a little bit more complicated, but it's not anything too bad. So just stay with me and hopefully it'll be fine. So we've got, as usual, the Na plus cations, and then we've got the Cl minus, we've got the anions. And then, as I said, we've got these H plus and OH minus ions just sitting in there as well. So what happens is, one thing quickly we might want to do is label what we've got. So the anode and the cathode. Something I recommend you do, if you're ever dealing with a question where it's not been labeled for you already, label it so that you know what you're dealing with before, because otherwise it might be difficult to work out where everything's going later. So as we said before, the chloride ions are negatively charged. They're the anions, so they're going to move to the anode. So we get them all here. And then similarly, the OH minus ions, which are the negative ions, they're going to move to the anode as well. And then on the other side, we're left with the Na plus ions, which are the cations, and the H plus ions. So once we get to this stage, we have to, so basically what happens at this point is we've got our reactants being produced, but normally, as we did before, we would have sodium being produced and chlorine being produced. But in this case, because we've also got the hydrogen ions and the OH ions together, that means that we're not necessarily always going to produce Na plus and Cl minus ions. So it could be something else. So the way we have to do it, the way we have to work out which one wins, essentially, is by following some rules. So at the let's start with the anode. So at the anode, it's quite simple. The OH minus ions will always win. So they will be the ones that are in our half equation, unless there are something we call halide ions present. And this just refers to ions which are in group 7. So this might include iodide ions, chloride ions, fluoride ions, etc. Anything that's in group 7 on the periodic table. So if they are present in the solution, they will be the ones that are in the half equation, and the OH minus ions will just be something called discharged. So the other one is discharged. So the one that doesn't win. So the OH minus ions are anions, and they go to the anode, as it is in the diagram. I don't know why group 7 ions always end in ides, to be honest. It's just a nuance of chemistry. With regards to your question about why O2 and H are separate, I'm not really sure. That's just the way I was taught. You'll probably learn about it way into the future, but for now you just need to know that H plus the cations and OH minus together make an anion. Is it always cathode? Yeah, OH minus ions will always go to the anode because they're always negatively charged, so they're always the anions. So you always have the OH minus ions on the anode and the H plus ions at the cathode. Is there a more practical term other than win? There isn't really, because you never need to explain which one kind of is success. Maybe you could just say is successful or is the one that is produced. But usually people just, it makes more sense to people when you say wins. Yeah, so a useful acronym that someone just posted is PANIC, positive anode, negative cathode. Actually, I'll write that down up here. Yes, they'll be recording when the thing ends, and there'll also be the PDF of this. So to continue, we've got the cathode as well. So at the cathode, what happens is the H plus ions will always win. Unless the metal reacting is less reactive than carbon. So if it's less reactive than carbon, that means that we're then going to produce something other than hydrogen ions. So with that in mind, So with that in mind, we can now work out what we're going to produce. Sorry, I don't know why I put carbon, it's hydrogen. I had carbon in my head from something else. So now we've got these two rules for the anode and the cathode. We can work out from our example of NaCl what we're going to produce at each electrode. So let's look at the anode first. We've got Cl minus ions, so that should be alarm bells inside your head for halide ions being present. So this means that they're going to win over the OH minus ions. So the reaction that we're going to get here is only with the chloride ion. So it's going to be the same one as last time. 2Cl goes to Cl minus 2Cl minus plus 2 electrons. Sorry, that's wrong. Oh, no, that's correct. And then at the cathode, we're looking at the H minus ions and the Na plus ions. So the H plus ions always win unless the metal is less reactive than hydrogen. But in this case, it's actually more reactive. So that means that the hydrogen ions will win. So we're going to have H plus goes to H plus H2 plus 2 electrons. Sorry. This is the right way around. So again, hydrogen is diatomic. So we are producing, so it goes from 2 H plus ions. They take 2 electrons to produce H2. And that is the electrolysis in aqueous solutions. So I'll give you 30 seconds just to get anything down that you missed. I'm conscious we need to move on to the other topics. So if you could just copy anything down quickly, it'd be great. Yeah, platinum is the unreactive electrode. Yeah, it's usually platinum, but it might be something else like silver. With the question about a generic half equation, if the metal is less reactive, you might see, well, let's just have a look at the reactivity series. So you might produce, yeah, copper, for example. So that would just be, so if we're looking at the cathode, so Cu plus 1 electron gives you copper, like that. See, it's actually Cu2 plus, so you would have 2 electrons to make 2 copper. So with your question about sodium, because sodium wasn't less reactive than hydrogen, that meant that it was just discharged. And then similarly for, no, so the one that's discharged is not the one that appears in the half equation. The one that appears in the half equation is the one that won, the one that's actually produced. So for the anode, chlorine was the one that was successful because it's a halide ion. So it's the one that gets, so the one where chloride ions are produced. Sorry, this is wrong. I thought it was wrong. My bad, sorry. And for the cathode, hydrogen won because sodium is more reactive than hydrogen, so it doesn't win over the hydrogen ions. And so sodium was just discharged and hydrogen was produced. Yeah, so the electrodes are inert. Yeah, as you said. Does that, hopefully that makes sense. I know it's quite a lot to cover in half an hour. If I had more time, I would explain it more carefully, but I'm conscious we need to look at the other topics now. So next thing we're going to look at is a lot more simple. Yeah, with your question about aqueous solution, yeah, it's always H2O, yeah. So now we're going to look at something much more simple, which is endothermic and exothermic reactions. We're just going to look at what they are, what the differences are between them, and then we're going to look at the 2 equations which you might use to calculate enthalpy change. So with an endothermic reaction, the generic equation for any, the generic definition for any reaction is just that it absorbs heat energy from the surroundings. So it's a reaction that absorbs heat from the surroundings. So it's taking in heat energy from the surroundings. So we've got an energy change from heat energy to chemical energy. So we're taking in heat energy to produce chemical energy. And delta Q, which is, delta H, which is enthalpy change, this is always going to be greater than 0, so positive, in an endothermic reaction. And we'll look at why that is in a second. And some examples of this kind of reaction might be the melting of ice, and evaporating water. So there is something called a reaction profile diagram, and that's something you might be asked to draw sometimes. So for endothermic reactions, the diagram which you would draw, so we have our reactants here, and then we have the reaction occurring, and then we have our products being produced on this line here. So we would annotate this by putting reactants here, products here. And then if you've done this before, you would annotate this as your activation energy, which we call EA. And then this is delta H, which is our enthalpy change. If you've not covered that before, if this looks confusing, don't worry about it, because it's something that you'll learn in another topic. So if it's confusing at the moment, just draw the diagram if you want, but if not, don't worry too much about it. The question about evaporating water is because water is currently a liquid, right? So when it's a liquid, it needs energy to become a gas. So it absorbs energy from the surroundings to then become a gas. It doesn't actually release energy. With regards to your question about the energy profile, so we've got reactants at a certain level of energy, and then we've got the activation energy, which is the energy required to actually get to produce products. And then, as you can see, there's less energy used to produce the products. There's less energy released. It's all absorbed. Okay, I'm going to move on to the next bit now. So we just looked at a reaction where heat is absorbed from the surroundings. With regards to your question about activation energy, unfortunately, I don't have enough time. I've only got an hour to talk about this stuff. So activation energy is something you'll learn in another topic, rates of reaction. So I won't give you the definition for now. So we just looked at absorbing heat energy from the surroundings. But now we're going to look at the opposite, which is an exothermic reaction. So it's a reaction where heat energy is released to the surroundings. So totally opposite from this one, delta H is going to be less than 0. So our enthalpy change is negative in this case. And we are having an energy change from chemical energy to heat energy. And an example of this might be a neutralization reaction, or a combustion reaction. And again, looking at an energy profile diagram. Just make that bigger. Where this is potential energy. This is the reaction pathway. In this particular case, we have our reactants, but then we're releasing energy so that there is a greater change in enthalpy. Yes, self-heating cans and hand warmers are an example of an exothermic reaction, yes, because you've got heat being released to the surroundings, so it makes your hands warm, yeah. Again, if you're not happy with the reaction profile I've drawn, I've really just drawn it for reference if you've already covered something like that. We don't have enough time to explain that, but I'm just kind of giving you a rough framework of what an endothermic and exothermic reaction is. Ice packs endothermic. I don't know, actually. I would presume no, because they don't absorb heat from the surroundings. I don't know. So with the delta H, which I've drawn here, again, might be something you're not familiar with. We'll look at it again in a second, but it basically means the change in enthalpy. So H is enthalpy, and delta always means change. Yeah, I don't know. If they absorb heat, then yeah, they would be endothermic. Basically, anything that absorbs heat is endothermic. Anything that doesn't is exothermic if it releases heat. So I'll give you just 10 seconds to screenshot that or take some notes if you need to, and then I'm going to move on. Yeah, take heat from surroundings, yep, so they're endothermic. Okay, so I'm not going to look at an example because we don't have enough time, but we're just going to look at the two equations that you would use to calculate Q. So usually you will be, with AQA, they'll usually give you the equation, but you'll have, so the first equation which we'll use is delta Q equals MC delta T. And this, so usually you'll be given perhaps mass and change in temperature, and C, which is specific heat capacity, is usually a constant, so it always stays the same. So to give you an idea of what these mean, this is the change in heat energy, and it's measured in joules. This is mass, which is measured in grams or kilograms. This is C, which is specific heat capacity. Specific heat capacity is the energy required to raise the temperature of 1 gram of a substance by 1 degree, but you don't need to know that. So it's in water, it's 4.18 joules per gram per Kelvin, but you'll usually be given that. With regards to your question about the Haber process, we're literally just about to move on to it. And then delta T is change in temperature. And so that will either be measured in degrees Celsius or another type called Kelvin, but you'll never need to convert. You just need to be given, just need to use the value given in the question. And then the second equation, which you'll sometimes use, so sometimes you'll be asked to calculate delta H, which we looked at before, which is the enthalpy. And so you'll calculate the delta Q, and then you'll use that to then answer the second part of the question, which is which is using this equation, minus delta Q over N, and that will give you delta H. So as we said, delta H is enthalpy, and this is measured in kilojoules per mole. So notice how we've changed the units to kilojoules. And N is moles, which is measured in moles. So make sure you convert to find the correct value as your answer, because usually you lose a mark if you don't. The question about triple science and is it for AQA? I don't know. I took edX class, so I don't know what it is for AQA, but if you check the spec, it will probably tell you if you need it. It will say something like know how to use calculations to find enthalpy. I would imagine you probably do need it. In fact, I think there's a question in the examples we're going to look at which actually does include that. So I think they give you the equation, but you still have to know how to calculate it. Yeah. I don't know if the second equation is used in combined science. With regards to the question about is the Haber process triple, it depends on your exam board. Okay, so those are the two equations. I know that was really quick, but we're now going to move on to the Haber process. So we're going to look at the key points, the equation for the process. Then we're going to look at why we need the process in real life. And then we're going to look a bit more about the process itself and how it happens. So here's a diagram of what happens. It might look a bit complicated, but we're going to go through it step by step. So the equation for the Haber process is nitrogen, which is a gas. So we take nitrogen gas, we react it with hydrogen gas, and this produces ammonia. So to write that in words for you, just in case, oh, that color doesn't come out very well, does it? Let me take a... So this is nitrogen, this is hydrogen, and this is ammonia. So this equation reaches something called dynamic equilibrium. So if you've not heard of that, just ignore the point for now. But if you have heard of it, obviously you'll understand what that means. Essentially, it's where the forward rate of reaction is equal to the backward rate of reaction. It's actually a reversible reaction as well. So you would have this symbol, meaning that it can go both ways. So the reactants can go together to make the products, and then the products can go together to make the reactants as well. I don't know if the Haber process is paper 2. You'll need to check with your specification. So the last thing we're going to look at for the Haber process is the actual process of the reaction, because it's something used in industry, which we use to produce fertilizer. So looking at the diagram, the first thing that happens is nitrogen and hydrogen are pumped through the pipes. Nitrogen is from the air, so it can just be extracted because it makes up most of the air. And hydrogen is obtained from natural gas. And then from there, we increase the pressure to 200 atmospheres. Now, an atmosphere is equal to 1,000 kilojoules, just to put it into perspective. So it's very, very high pressure. And that happens at this point. It's not the same as fractional distillation, no. And then from there, the gases are heated to 450 degrees. These temperatures are important because they'll usually ask you to actually specify the temperatures. And then it's passed through a tank. Which has an ion catalyst. Now, a catalyst is essentially something that basically makes a reaction happen more quickly without affecting its composition. So we can use ion catalysts to make the reaction happen faster, but it doesn't affect the ion when it can be reused. So once we've done that, we cool the reaction mixture in the cooling tank. We remove the ammonia liquid, and that's what's extracted. And then the gases which are produced, the H2 and N2, as you can see, they are recycled and the reaction just keeps happening. And that's where the dynamic equilibrium comes in, because some of you will know what that is. The reaction can keep on going because the ammonia will keep producing nitrogen and hydrogen, and nitrogen and hydrogen will keep producing ammonia. It goes back and forth. So that's a whistle-stop tour of the Haber process. The other thing which you need to know is what it's actually used for, which is often a question that comes up in most papers. So the Haber process is needed for fertilizer. So it makes fertilizer, which is needed to grow crops quickly. And for a higher yield. And that just basically means that it's used on farms a lot to make sure that they can grow enough crops that they need to sell them. And then if they can yield more crops, if they can get a greater quantity of crops produced, then that's obviously better for them because they can make a greater profit and produce more food. So if you have any questions on anything we've covered up until now, just let me know in the chat. I totally appreciate that we spent a lot of time on electrolysis and not as much time on the other two. Unfortunately, it was quite a lot of content for 1 hour, but this will all go back to you, these annotations, so you can copy up the notes later. And obviously, hopefully this answered some of your questions or something you didn't understand. Your question about dynamic equilibrium, if you haven't done it yet, don't worry about it. Just wait until you're taught by your teacher, because I don't have enough time to explain it to you fully now without going into a whole another topic. Just to let anyone know that was on the course that's starting at 8 o'clock. I'm just checking now, the one on organic chemistry, that was cancelled because of the storm. Okay, so thank you for joining me. If you want to stay behind, I'm going to brief for about 15 minutes. I'm just going to go through the exam questions because I appreciate we haven't got onto those yet. So if you want to stay and go through those with me, then feel free. But if you're happy with all the content that we've done, feel free to leave. Thank you for joining today. I presume you'll get your money back for the other, yeah, I'm sure you will, for the other meeting, although I'm sure it will be rescheduled. Yeah, so thank you. I'm going to now get started with the exam questions. So if you just want to stay for those, feel free. If you don't, that's absolutely fine. Thank you for joining. So we're going to look at a question about electrolysis first. This is taken from an Excel question, but obviously everything's transferable to different exam boards. The questions will remain very similar. So we're looking at something quite similar to what we did before, but obviously the diagrams given are always going to be very similar to any other that you'll see. They all have the similar basis of electrodes, your electrolyte solution, your positive and negative electrodes, all that sort of stuff. So you just need to look at it. If it's not labeled, label it so that you understand what everything is, and then you can start with the question. So the first thing that we looked at was what are the electrodes made of? We looked at what kinds of metals that might be used. And we mentioned that it would be platinum because this is less reactive. So it would be the same for both. You can mention platinum. The one that they've actually given in the mark scheme here is graphite, but they will accept any that's correct, basically that is unreactive. Yeah, everything's been recorded. Everything up until the end of this meeting's been recorded, so you'll have this. So basically anything that's unreactive, you can put there. They want graphite in this particular instance, but platinum would not be incorrect. Then the next question says, explain why the operating temperature would need to be very high if pure aluminium oxide were used as the electrolyte. Now, this is because aluminium oxide, if it's added to the electrolyte solution, we need it to be molten, we need it to be liquid so that it can actually react in the solution. So therefore, we're going to need a very high temperature in order to make it become molten. Yeah, so a lot of energy required to make it molten, and therefore we need a high temperature. Hopefully that makes sense. So then it says, describe how the operating temperature is kept low. So once we've got this very high temperature, once we have these molten solute, once we have this molten aluminium oxide, we need to, once it becomes molten, it's dissolved with water. So when something is dissolved with water, water is going to have a lower temperature than the aluminium oxide. Now it's molten, and therefore that's going to keep the temperature a bit lower than it was before. So hopefully that makes sense. So moving on, now we've been given a half equation of aluminium. So let's dissect this quickly. So we've got aluminium 3 plus. So this is obviously a cation, and it's gained 3 electrons to become just aluminium on its own. Right, guys, can we keep the stuff in the chat based on chemistry? Because if it's not, then I'll just remove you. Sorry about that. Okay, so moving on. So we've got aluminium, which is our cation, and we've produced aluminium. So it says, what type of reaction is occurring at the negative electrode? So the negative electrode is our cathode, which is, so the cations go to the cathode. And we are gaining electrons to produce aluminium. So if we look back at our acronym here, we have oxidation is losing an electron, and we have reduction is gaining an electron. So if we look at this particular example here, we've got aluminium 3 plus, and that gains 3 electrons to become aluminium. So if it's gaining electrons, it's going to be a reduction reaction. So because this is 3 marks, or is it 3? It's 2 marks, sorry. We need to be able to explain that, not just say it's a reduction reaction. So the first mark would be a reduction reaction is occurring. And this is because aluminium is gaining three electrons. And that's it. So first mark would be for saying that there's a reduction reaction. The second would be for explaining that that's because you gain 3 electrons. Your question about what's a cation. So cation is an ion which is positively charged. So in this case, because aluminium has the 3 plus sign, I know you can't see that very well, but because it says 3 plus, therefore it's positive ion, so we call it the cation. Is a redox reaction the same as a reduction reaction? So a redox reaction is something that's either reduction or oxidation. So that's what we kind of use to shorten reduction and oxidation. So reduction, oxidation reaction. So a redox reaction would be an example of a redox reaction, just like an oxidation reaction would be an example of a redox reaction. Now we're going to describe the, actually, I think I'll leave those questions there. I will write up the answers from the mark scheme. So when you get the PDF, you can see what the other answers were and how I went about answering them. If anyone wants to quickly go over the endothermic and exothermic, could you just put your thumbs up or raise your hand or something? Because I don't want to go through it if none of you actually feel the need to. Yep. Okay. Some people want to, okay, fine. Yep, we'll go through it. If you want to hang around for there will be one afterwards on the Haber process, then just stay behind quickly and we'll cover those. So here we're looking at endothermic and exothermic reactions. So we've got an equation, we've got a reaction going on here where we add zinc powder to copper sulfate. And that is going to be an example of energy being released. So that's going to be an exothermic reaction. And we not only know that because it tells us that energy is being released, but we also can see that from the temperatures. So as you can see, we start at 21 degrees, but the temperature increases. So if the temperature increases, we're releasing more heat. So it must be exothermic. So the first part of the question is relatively simple. It's just asking us to calculate the change in temperature. So we're doing the highest minus the start. So that's 32 minus 21, which gives you 11. So the change in temperature overall is 11 degrees. For the second part, we're looking, it tells us that it's exothermic, but we already knew that. And it says, how can you tell from the student's results that the reaction is exothermic? So that's asking us to explain why we've decided that it is exothermic. So as I said, it's because we start at 21, but at some point in the reaction, it doesn't say the end, but it says at some point we reach 32 degrees. So the reaction temperature must be increasing. So we can just say because the temperature increases during reaction, meaning heat energy is, sorry, meaning heat is released. Let me say heat energy. Okay. So two relatively simple questions so far. Oh, yeah, I've missed a part down here. So now going back to the calculations which we looked at, did you have a question, Nat? Or are you, if you still just got your hand up from, yeah, okay, cool. So as we said before, we're now looking at an example of Q equals mc delta T. And we need to calculate that. Now, one thing which you might be thinking is this says volume, but you've written mass. It actually doesn't matter because 1 centimeter cubed is equal to 1 gram. So if we had something that was 100 centimeters cubed, which in this case it is 100 centimeters cubed, it's just going to be 100. It's just going to be 100 grams. So we are being asked to calculate the energy released in joules. We know the temperature change, so we know delta T, that's 11 degrees. We know the mass. Which is 100 grams. Oh, sorry. Or 100 centimeters cubed, but we're just using numbers in this case. And we have been told that C, which is our specific heat capacity, is 11. Sorry, not 11, 4.2. So it's a quite simple equation. We're just going to do mass times C times delta T. So 100 times 4.2 times 11, and that should give you 4,620 joules. And that will give you 2 marks by doing all of that. So your question could ask what app you use. I'm using GoodNotes for this. Yeah. So that is how you go about doing a calculation question. As you can see, it's a relatively easy one in this case because we're just looking at the first part of the 2 equations I showed you, but still useful to know. And now we're looking at an energy profile diagram. So what we were looking at before for endothermic reactions and exothermic reactions, this. So as you can see, we've got a similar idea of that here. Oh, sorry for the scrolling. So the question is asking, how can you tell from the energy diagram that the reaction is exothermic? So firstly, we need to work out what A, B, and C are actually referring to. So A is what we were looking at before as activation energy. And then B is something we call delta H, which is always the distance between the products and the peak of the reaction. So delta H is going to be our enthalpy change. And we know that it's going to, in this case, we know that, but in this case, it's actually much more simple than that. We can use delta H to explain it, but in this case, we just want to say that the level of the reactants is higher than the level of the products. That is the only thing you need to say when you're explaining why an exothermic reaction is not an endothermic reaction. So the energy level of the reactants is higher than that of products. And then it says which arrow shows the activation energy in figure 2. So this will now come in useful for the annotations we did before. As we said, it was A. Okay, so hopefully that all makes sense. We moved a bit into reaction profiles, which we didn't really look at. So if you weren't too sure about any of that, that's not too much of a problem. But if you're happy with all of that, and you're not, and you don't need to see the question about the Haber process, then feel free to leave. We'll just quickly do the 4 marker on the Haber process. And if you, but if you don't want to stay for that, then you're free to leave. So we are looking at a similar, slightly simplified diagram of what the Haber process is. So again, we've got this pump, which is pumping all those nitrogen and hydrogen gases, increasing the pressure to 200 atmospheres. So we're going from essentially 1,000 kilojoules to 200,000 kilojoules. And then it's being reacted to produce the ammonia, and then we're recycling the nitrogen and hydrogen. So the question is asking us, what effect, if any, does the pump have on the pressure of nitrogen and hydrogen? So as we said, we're increasing the pressure from 1,000 to 200,000 kilojoules. So obviously the pressure is going to increase. Now we've been given the word equation for the Haber process, which is nitrogen plus hydrogen makes ammonia. And it says if in the reactor, only a small amount of nitrogen is changed into ammonia. And it's asking us to explain why that happens. And so the answer to that would be that the reaction is reversible. Now, the reason why it's because the reaction is reversible is because it's, so if you don't understand what a reversible reaction is, that's okay. But essentially, we are using nitrogen and hydrogen to make ammonia. And then we are, then with a reversible reaction, similarly, the ammonia can be used to make the nitrogen and hydrogen. So if we've got a reverse reaction happening, that's going to mean that we produce nitrogen and hydrogen once we've produced ammonia. So it's going to, a lot of it's going to be converted back into nitrogen and hydrogen. So we only obtain some ammonia because some of it's already been converted back. So when it's a reversible reaction, we're not always going to get all of the ammonia because it might change back. That's essentially why. Then we're looking at the cooler, and it says in the cooler, the mixture of gases is cooled. And it says the cooler turns the ammonia into what? And as you can see, it's actually even written, it says it's changed into a liquid. We're producing liquid ammonia. And then it says, what happens to the unreacted nitrogen and hydrogen from the reactor? As we looked at earlier, it's just recycled. So it takes part in the reaction again. Does anyone have any questions about anything I've done in the past hour and 20 minutes that they want to ask, or anything else to do with the topic or studying in general. If you do, just let me know. If not, thanks for joining. I hope that was useful, and have a good evening. Do we need to know that it's turn? I presume you will. I don't know. I've never had a question because it was taken out of my course. But I would presume so, yes. Is it only used to make? Well, with the reversible reaction, nitrogen and hydrogen will make ammonia, and then ammonia will make nitrogen and hydrogen, and then that could then make ammonia again. So it's just a continuous cycle. Hopefully the recording and PDF will just be sent to you afterwards. But I don't know, because I have to send it to Ishan, and then he sorts all that out. So I'll just send it to him. Hopefully he'll send it to you. But if he doesn't, I'll try and remind him to. How much revision should you do a day? It depends on a lot of things. It depends on, one, what you're aiming for. So if you're aiming for a 9, then you're going to want to do more than if you're aiming for a 7, for example. It depends on what subjects you actually want to do well in. If you want to do a career in chemistry, ideally you would strive to get a 9 in all of your subjects. But if you think that actually I really want to just get a 9 in chemistry, I'm not too worried about everything else, then obviously spend more time on that. But and then it also depends on, have you got tests coming up? If you have, I used to allocate about, in a week I would allocate about 5 hours of my time to chemistry when I've got a lot of time to revise. But yeah, I mean, it really varies. Just, think about what you want to do, what you want to get done, how much work you think you need to do to understand what you don't understand, and how much practice you need to do, and then work it out from there. I wouldn't say there's a definitive number of hours. I would never say do like 2 hours of chemistry a night or 2 hours of biology or whatever. I wouldn't do that. Surely nothing would be made then, always more. Well, no, because some of the ammonia can be extracted before it's converted back. Not all of it would suddenly be converted back. It's kind of constantly going, so some of it can be isolated. What did I get my GCSEs? I got a 9 in everything apart from maths. I got an 8, and I got a 7 in further maths. Oh yeah, Pomodoro timing is really good. Yeah, lessons should be Pomodoro based. Yeah, that's true. I would recommend that if you're revising. Does anyone have any other questions? I'll close the Zoom if not. So yeah, feel free to ask them if you do, but if not, have a good evening. I'm using an iPad Pro. The 11. 12.9 is too expensive. The M1, actually, I replaced it recently. Okay. Thanks everyone for joining. I'm going to close the Zoom now. Have a good evening.